Here's the review for chapters 16, 17, and 18. And I think I'm going to divide this into 3 videos, one for each chapter, just so that it's have a nice break. So the color order of the visible spectrum from small to large and from large to small wavelengths. Well, color is really defined by its wavelength, and we often think of Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. The red has 700 nanometers, and the violet is about 400 nanometers. So that's from large to small. But when reading the wavelength from small to large, from the 400 to the 700, we're going to have to reverse that, and that's why we have the VIB-GYOR. So the violet's about 400 and the red is about 700. That's the approximate wavelengths for the red and the approximate wavelengths for the violet. And again, NN and M is nanometers. So we have a luminous body versus a illuminated body. So a luminous body, this is what emits light, like the sun. And an illuminated body is like the moon. The illuminated body receives the light and either absorbs or reflects it. So it receives the light and reflects that light. Some of it, of course, will be absorbed, but a lot will also be reflective. Numerical relationship between distance and the intensity of light. If you increase your distance by a factor of 3 times, what happens is the light intensity is going to go down, or the illuminance is going to go down by a factor of the distance squared. So you're going to decrease the illuminance by 1/9. So here's the formula. The illuminance, which is the capital letter E, is inversely proportional to 1 over the distance squared. And again, if you remember, this is related to the inverse square law, because we're looking at the light, the number of photons that are coming from the source, radiating outward and hitting that surface at a particular distance. And hitting that source at a particular distance, if you remember that sphere, we're looking at the surface area of that sphere that the light is landing on. And area is going to be length times width, or distance squared. Difference between transparent, translucent, and opaque. So transparent, remember, parent means to bear. So what happens is, in transparent, this is like a window. You get the light coming through, and you also have the image coming through. Translucent, loose just means like lux or Lucifer, means light going across. That's what that means. So in translucent things, just the light is going across. If you can imagine smoked glass, those are used as privacy windows for your front door, so that people can't look in and see what's happening in your living room. And of course, opaque, you have no light going across. This is like a wall, no light, and of course, no image is going to be born across. What happens to white light when sent through a prism? You get all the colors of the rainbow. You get a continuous spectrum. Remember from chemistry, there are no gaps or spaces that are going to be in between the colors. One color transitions to the next. The 3 primary colors that produce white light when combined Remember, we have red is a primary color, blue is a primary color, and it's not yellow, but it is green. Light is different from pigments. How light is polarized with a polarized filter and the types of waves that pass through it. Polarized filters are made out of these polymers, and these polymers are all oriented in one direction. So the polymers are in one direction, and it allows those light waves to pass through in their orientation. So light passes through in the same direction. Meaning all the other wavelengths are going to be blocked except those that are going up and down. If this was tilted 90 degrees, it would block all those that are coming in vertical. It would only allow those coming in horizontal. What will happen to light when using two polarized filters that are perpendicular to each other? If you remember, if you have those, we had that when we shifted those. When they're in the same orientation, the light goes through. When you shift them 90 degrees, it blocks them. So it blocks all light. What is the connection between polarized filters and reflections? Actually, we went out for a hike the other day with our kids, and we went to, I think it was just the Natchez River, and I was wearing my glasses and I'd never worn them next to a river before, and it was sort of freaking my eyes out. But then I noticed that, oh, these must be polarized lenses, because you can really, when I took them off, you can't see under the reflection, but when you put them on, you can really see that reflection. So let me go ahead and remind you how that works. So when light comes in to the surface of the water, so here's the water right here, it's coming in with scattered waves. Okay, now these waves are coming up and down, left and right in all orientations. So the light's coming in and it is scattered light. However, when it hits the surface, that light reflects off of the surface, and when it does so, this light is then polarized, meaning that it's in one orientation. So if you're wearing sunglasses, here's the glasses, and here is your eye behind those sunglasses. What happens is the polarized light, when it reaches your glasses, gets blocked. However, what you're able to see is you're able to see the light that is coming off of these objects that's not polarized underneath the water, and those rays of light can come to your eye. So here is the polarized filter, or your sunglasses. So when you have your polarized glasses, this blocks the reflected light. Blocks the reflected light. Which is the reflection, but you can see under the water. What's the connection between a polarized filter and reflections? That's what we just went over there. So here's some calculations. So here's the formula, which is very similar to the speed of light. The velocity, or the speed, is equal to the wavelength times the frequency. So this is the wavelength, and the wavelength is measured in meters. And this is the frequency, and the frequency is measured in hertz, which is 1 over seconds. And here is the speed of light, and that is a constant at 3.00 times 10 to the 8th meters per second. So you're going to have to calculate the, it's going to be providing the wavelength, you're going to have to calculate the frequency of the color. There's going to be a problem with luminous flux and the units of each. So the illuminance is based upon this right here, okay? And the luminous flux is simply the output. This is the output, the amount of light. For example, 60 watts versus 100 watts. So it's the output of light. And this is measured in lumens. If you remember, we discussed LED lights versus the regular lights. You can have a 60-watt equivalent LED light that may only be using 7 watts. But they're both putting out the same number of lumens, which is the light output. So this is measured in lumens, and lumens is LM. I'm going to just do a cursive LM so you're not confused with 1 meter. So it's LM. Okay, so your illuminance, not your luminous flux, but your illuminance, this is your illuminated, how much light is it being received at a distance, which is based upon this formula here. So you have your luminous flux, which is your LM, over your distance squared, let me italicize that, which is over distance squared, which is meters squared. Lumens over meters squared will give you lux, or abbreviated LX. Calculate this. So again, your flux is your capital P. And again, this is relating to the inverse square law, where this is going to be the radius of the sphere. So if r equals 1, your radius equals 1. You're looking at how much input of light is going to be received at this distance, at that radius. Okay, and then how much is it going to be received at 2 meters? Okay, so we're not calculating all the energy because all the energy that would be received here would be equal to the luminous flux, which is being put out, but we're looking at a very particular point on this sphere, which is the surface area. That's it for chapter 16.